is defined as, first let me write formula. Alpha is equal to, this will be delta L by L into delta T. Change in length per unit rise in temperature. It is defined as ratio of change in length per unit rise in temperature. I think definition, or else if you want, is defined as when the rise in temperature. So there's the one formula. In books, we have one more formula like this. Alpha equal to dl by L dt. This is nothing but alpha average. Getting this one? This is like a instantaneous. Are you getting this one? Even alpha will be variable. I have for like most of the metals, this in fact will vary with the temperature, but we assume it to be constant or a range of temperature. So what we discuss, all our numericals will be based on this, the first one, average value, not instantaneous. If alpha is variable, use this particular formula. If I say for a given object, alpha is a constant, use this particular formula. I think, where do you have come across all these things? Instantaneous velocity, average velocity. Similar to that one, similarly here. So what all we discuss will be the average value. This one, if alpha varies with the temperature, no, take help of this particular formula to find out the unknown things. Like this, we define this quotient of what can be unit for this per degree Celsius, because delta L by L, the units will cancel. So per degree Celsius will be the unit for this one. Now, so what is actually delta? So this will further take the expansion. So delta L equal to L alpha delta T. What is the delta L? Change in length. Let me start with this. So this was the length L. Now L plus delta L. This was the temperature T1, T2 degrees Celsius. So what is delta T? T2 minus T1. T2 minus T1, it will come. So this delta L, what we can write it as further. So delta L, anything can we write it here? This was the basic definition, no? Or we'll write in another form. Delta L, how you write final minus initial. Let me do right like this. So L2 is equal to L1 here. Let me call this length as L dash. L dash minus L equal to L alpha T. So L dash is equal to L plus L alpha delta T. So this will be 1 plus alpha delta T. This will be the final length. L dash will be how much you write? L plus delta L. Or delta L, you can, I think either of thing, you can use either of the formulas. Okay, there's a formula for as you rise the temperature of a rod by an amount, by an interval, so by an amount delta T, the final length is given by this particular formula. So what is alpha? Quotient of linear expansion will be different for different material. Alpha will be different for different material. Next again, alpha more, what does it mean? The body is sensitive to variation in temperature. If alpha more, then slight change in temperature, there'll be appreciable change in length of the body. So therefore, in applications where I want to measure change in temperature, I'll go for higher value of alpha. Now I want a body which will not respond for change in temperature. Then I should prefer the lower values of alpha. Most of the metals, what happen, they have good values of alpha. Agree this, so it will be different for different materials. Okay, this is about the quotient of linear expansion. Now again, if you look at the isotropic and isotropic, there are, we do get so isotropic substance. So if you take the isotropic substance, okay, this we have x, y, z. I took a cube which is having a side length L. If I raise the temperature, then what will happen to this cube is it will expand. It will expand uniformly in all direction. It will expand uniformly in all direction. So at higher temperature, this will be the dimensions. L dash, L dash, L dash. So how much it will expand along x-axis. In the similar way, what happen, it will expand along y-axis. So the expansion will be same in all directions. So alpha x, you write alpha y, alpha z. So you measure the length of the each length of each side of the cube. It will be same. So therefore, what does it mean here? Alpha x equal to alpha y equal to alpha z. This is what happens for isotropic substance. I'll write it here. So for isotropic substance, what does it mean? It will have the same behavior in all directions. All direction means here 3 directions. So how much it will expand along x, equal amount it will have the expansion along y and also along z axis here. So what shall we put it isotropic? It will exhibit same property along all directions. This is about the isotropic substance. Anisotropic substance. So what do you mean by anisotropic? Where alpha x not equal to alpha y not equal to alpha z. So if I have a cube, this is length. Let's take this one. So this is the x-axis, y-axis, z-axis. I think no longer it will be cube. It may become cuboid. This will be alpha x, alpha y, alpha z. Here alpha x not equal to alpha y, not equal to alpha z. So if I write this length Lx, look at now, Lx greater than Ly, and shall we put it here? No. So the same material. So the material open, don't think that one side iron that one. It's an anisotropic substance. It will exhibit different properties along different direction here. Suppose say this is 10 centimeter, 10 centimeter. Then this will become how much here? Say like a 12 centimeter. Here it will be say like a around 10.5 centimeter. This will be around say like a 11 centimeter. So what is this substance? It is having different expansion along different direction. We may get numericals related to this also. We have to be careful. So what all we discuss will be all our applications are based on isotropic. Any numerical they may ask also on an isotropic substance also. You have to be a little bit careful. Getting that idea? This one? Okay, now this is about the quotient of linear expansion. So quotient of, we'll define next one, quotient of area or superficial expansion. Quotient of area or superficial expansion. So if we have a disk, let this radius be r at temperature T1 degrees Celsius. Then I'll increase. It has become r dash. The radius got increased here. So you can look at the area. So this is called like a superficial expansion. So this will define this as beta. So this is how you define change in area by initial area by change in temperature. Or therefore you can write it as A dash is equal to A into 1 plus beta delta T. Change in similarly how we define area expansion, area or superficial expansion. For isotropic substance, what you write? For isotropic substance, alpha x equal to alpha y. So therefore, what is beta? 2 alpha. For anisotropic, you cannot write beta equal to 2 alpha. Okay, I think in numericals, you have to be careful about this condition. Means if a isotropic substance, if the circular disk, I'll change this one. No. So how the numericals will be for you is, so as you rise the temperature, definitely what will happen, its radius will increase. Fine. So earlier it was having radius r. Now it will become r dash. This is a temperature T1 degree Celsius, T2 degree Celsius, where T2 greater than T1. This is strictly what is alpha X equal to alpha Y. Isotropic substance it is. Anisotropic, any condition. I think this content I'll move it there. For anisotropic, any conditions can be put it. This was the alpha X not equal to alpha Y. So how the substance will be? I think it's going to take a shape of elliptical, am I right? Why it will become elliptical? Because alpha X not equal to alpha Y. How much it will expand along x-axis, that much it may not expand along y-axis. This will be very difficult to study such thing, that one. So usually we prefer this one. So it has become disk. No, you should not call this one. Ellipsoidal disk you can call it. If alpha X greater than alpha Y, so definitely this will become, x-axis will become semi-major axis, y-axis will become minor, semi-minor axis. If alpha Y greater than alpha X, the body should expand more along y-axis than along x-axis here. So small start from initial basics. No, you do get very best questions available here. Topic is, I'll finish off theory now, quotient of one more, and rest all everything is application. Applications are very wide. Almost this small topic, this formula, it is linked with more than 10 different topics: elasticity, friction, rotation mechanics, conservation of angular momentum, fluid statics. Like that, it's a unlimited wide number of applications will come. Okay, this is about coefficient of, now we'll go for next one, coefficient of volume expansion. Coefficient of volume expansion of the material. So this will write gamma. So this will be defined as change in volume by original volume by temperature. So then delta V, we can write it as V gamma delta T, or the final volume should be V into 1 plus gamma delta T. For isotropic substance, gamma will be alpha X plus alpha Y plus alpha Z. Okay, for 3D objects expansion, so you use this particular formula, gamma equal to 3 alpha. Like this will define coefficient of volume expansion. Okay, let's do one thing. So there's a body of mass M, a temperature T1 degrees Celsius. It's having a volume V1, density ρ1. I'll rise the temperature. What do you expect? I think it will expand, no? Let me shade like this. Yeah. Now the body will expand. Now tell me what will happen to the density of substance. First, let's start with mass. Anything will happen to mass? No. The volume, it will T2 greater than T1. So volume will increase. So the density what happen must decrease here. So we'll begin like this. Initial mass equal to final mass. So what is V mass equal to? Rho 1 V1, rho 2 V2. Now what is V2? You can write it as V1 1 plus gamma delta T. So therefore rho 1 equal to rho 2 1 plus gamma delta T. Or what is rho 2 is equal to rho 1 1 plus gamma delta T. What do you expect the density of substance will decrease, no? Or binomial expansion 1 plus gamma delta T minus 1. As gamma, what is the order of gamma? 10 to the power of minus 6. So therefore this quantity will be very small, product of these two. So from binomial expansion, neglecting higher order terms, actually what you get next plus gamma delta T whole square minus gamma delta T whole cube. As gamma is very small of order 10 to the power of minus 6, neglecting higher order terms, I'll end up with this much here. So this will be very widely I'll be using here. So therefore, as you rise the temperature, what will happen to density of substance? In general, density of substance, either let it be solid or liquid, density of substance will decrease. Mass will remain same. This is something very important. The mass of a body will not change on rise in temperature. I think this is something very important. Note. Mass of a body remains constant. This one, it will not change. So why, if temperature rises, what will happen? If temperature changes, mass of a body will not change. So this is something very, very important, that one, which will help us a lot in numericals. That's what I mean to say. Oh, account to me, your topic got over. Rest on everything what happened. Now we have to proceed for the different types of numericals related to this. This is only theoretical. So you read any number of times, this is theoretical information will be available and you can manage. So now the applications. Applications means thermal expansion applications. So as applications, I'm going to mix with what? First with the thermal expansion, basic thermal expansion problems. Then I'll link with the fluid statics. Then with the springs, elasticity, rolling motion. I think it's unlimited. Where all I want, I will introduce this concept. So you have to pick up a numericals related to of different kind.